I think. Yeah, a video just for 2 questions. Again, we'll take them a couple at a time. These are quite challenging. This is question 3 on page 246. So it says the small cone has a base radius of 7 centimeters. I'm going to try and draw that in. So from there to there is a 7, and the larger one has got a base radius of 14. So if I've got 14 there, that's a 14. And radii, of course. Now the little one's got a height of 10 centimeters, so try and draw that in carefully. There's your right angle there, so there's 10 centimeters, and this one's easy to draw because it's bigger. There's your right angle there, and that's 20 centimeters, isn't it? So all these numbers have units in centimeters, all these numbers here, right? So 10, 7, 20, 14. Right, find the volume of each cone. I did say I'll be using yellow, didn't I? Right, so the volume of cone, what's it called? Volume of small cone, there you go, vol small, is going to be 1/3 of pi times radius squared times the height. Just substitute it in, so it'll be 1/3 times 3.14 times the radius is 7, so it's 7 squared, multiplied by the height of 10 centimeters, and I made that 512.9 centimeters cubed. Please note 3D cubed. We'll do the other one now. Work out the volume of the big one. I'll just work underneath here. So volume of the large cone is still going to be 1/3 of pi times radius squared times the height. So it'll be 1/3 multiplied by 3.14 multiplied by the radius squared, which is 14 squared, multiplied by the height of the big cone, which is 20. If you're worried about thirding something, don't. Just go 3.14 times 14 squared times 20, then divide by 3. Same thing, isn't it? And that will give me an answer of 4,102.9 centimeters cubed of volume. So that's part A done. Now part B I'll do on this side here, and I might just change to red just for a bit of variety. Now, what fraction of the volume of the large cone is the volume of the small cone? In other words, I'm going to compare the volume of the baby one here with the volume of the big one there. So volume of small compared to volume of large, basically. Well, what fraction do we have? It's going to be 512.9 divided by 4,102.9, and that's going to give us, well, I worked it out, 0.125. In decimals, it's always bang on, and we know that's going to be 1/8. So what fraction of the volume of the large one is the little one? It's 1/8 of the size. Now that's great, but I'm going to prove to you that I didn't need this at all to work out part B. And in fact, what this does is warm us up for question 4. This is in fact question 3, but this method will in fact be used for question 4. Now look at this. Look at the linear ratio. I'll change to blue just to make a different issue of it. Look at the linear ratio of radius to radius. I've got 7 to 14, which is of course 1 to 2. So the linear ratio from small to big is 1 to 2. But look at the heights. I've got a ratio of 10 to 20, which is also 1 to 2. Obviously these are similar shapes. This one is clearly the enlargement of the small one by scale factor 2. Now I'm going to use that to do part B. The question is, what fraction of the volume of the large one is the volume of the small one? Now look, do you remember this teaching from previous topics? The linear ratio, let's just state it, I've just proved to you in 2 different ways, is 1 to 2. Do you remember that the volume ratio is this? It's going to be 1 cubed compared with 2 cubed. And 1 cubed of course is 1, and 2 cubed of course is 8. Therefore the little one has a volume of 1, whereas the volume of the big one is 8 times as large. Therefore I get my 8th that way as well. Okay, that's beautiful, isn't it? So I could have worked out part B without the knowledge of the volume of the small and large cones. I've gone straight into this volume ratio, area ratio type topic we've done before. I can't remember what it's called actually, but still, there it is. It's 1/8, proved to you quite simply. Right, that prepares us nicely for question 4, and there's the 2 answers then. So volume of small, volume of large, the fraction of small compared to the size of the large one. And of course we could have just divided two numbers anyway. Volume of small divided by volume of large equals 1/8, but I've proved to you in a much neater, elegant way that it's the case anyway, just by looking at the ratios of the linear heights or the linear radii. Right, question 4. I will use that same technique for here because I think that's what it's leading on to. This is question 4 then on page 346. Two spheres. I don't even have to draw them, but I will. Two spheres. There we are. That's a little sphere there. That's me trying to make it look all 3D. And I'm told the radius is 2 centimeters, and a bigger one here. I'm trying to make it look bigger. There it is. That's behind, and the radius is 6 centimeters. So this is sphere A and this is sphere B. I'm doing question A. The ratio of radius of A to radius of B. Okay, radius of A is 2 to 6, otherwise known as 1 to 3. So in other words, in terms of linear ratios, this is 3 times as big as the smaller one. Alright, in terms of linear ratio. Now for part B. The surface area of A and the surface area of B. Now look, we can work out the surface area of each sphere using the formula, and I'll write it up here. So surface area is going to be 4 times pi times radius squared. I could work it out for each one and then simplify down the ratio. I'm not going to do that. I'm going to do it the clever way. I'm going to take the linear ratio. Okay, so I'm going to take the linear ratio like that, 1 to 3, and then I'm going to square it, because if you square each part, you've upgraded each one to area. So 1 squared is going to be 1, and 3 squared is going to be 9. Therefore, in terms of surface area, the big one has 9 times the surface area of the small one. Okay, so that's really, really straightforward, and that is of course the area ratio. And this one was the linear ratio. It's not surprising that we're going to do the volume ratio now for the last part. So to do the volume ratio, then you take the original linear ratio, 1 to 3, and cube each part. So 1 cubed is 1, compared with 3 cubed, 27, and that's the volume ratio. Great topic to revise. Look at that. All I've done is increase the radius of the small one to the big one. It's basically 3 times as big radius wise, or linear dimension wise, or the diameter of the small one is 3 times as small as the diameter of the big one. But as soon as you start talking about surface area, everything becomes squared again, doesn't it? So 1 squared becomes 1, 3 squared becomes 9, and already my surface area is 3 times as big it's 9 times as big as the surface area of the small one, A. When it comes to 3-dimensional ratios, it's still 1 to 3 linearly, and then if you cube each part, 1 cubed is 1, 3 cubed is 27, but the volume, the amount of storage space inside that little empty football, or it could have been a solid ball bearing, anything, but the volume inside there, or the capacity to hold, say, a fluid in there, is 27 times as big as the little one, which is fascinating. All we've done is made the radius 3 times as big, the surface area became 9 times as big, and the volume became 27 times as big. So here's the 3 answers: linear ratio 1 to 3, area ratio 1 to 9, and finally volume ratio 1 to 27. I find this topic really fascinating. Anyway, so that's that. We've applied these old topics to shapes and space, and we're going to move on with the videos a little later on. But that's those two done, question 3 and question 4, and I'll see you very shortly.